One could ask the question, why does the world have patterns in it?
Mm-hmm.
And if somebody were to ask me that question, I would say, that's the deepest question I know of. And I don't think I'm going to live to know the answer. Of course, someone who believes in God might say, God made the world patterned. Someone who believes in laws, well, he could say that the laws make the world patterned. Someone who believes in non-Humean laws could say that non-Humean laws make the world patterns. But what's the next question you're going to ask that person?
Who made the non-Humean laws?
No, these are non-Humean laws, right? Who made the laws, right? Why are there laws? So this is like an ultimate question. It's the kind of question that only philosophers will really spend any time with. I mean, children ask this question sometimes because children are sort of natural-born philosophers. At least some of them are. There's a film directors named John and Ethan Coen. They've made many, many great movies. But the movie that I like most by them is called A Serious Man. It's actually about a physicist who's going through a midlife crisis. And in the movie, in the film, there's a minor character who's scribbling in a book. And somebody asks him, what are you doing? And he says, I'm composing the Mentaculus. So then the person asks him, well, what's that? And he says, it's a probability map of the universe. So when I saw the movie, I realized that what I'm doing is making up a probability map of the universe. So I decided to call the project I'm working on the Mentaculus.
Hey guys, welcome to an episode of Wandering Thoughts. Today I'm joined by Professor Emeritus Professor Barry Loewer. Professor Barry, thanks for joining us. It's a pleasure to be talking to you, and I appreciate your time. I think it's good if we begin just by you introducing yourself to us and the audience listening, and perhaps telling us a little bit about your areas of expertise too.
So I should say something about me and how I got into philosophy and that.
Mm-hmm.
Okay.
Yes,
Well,
please.
so I'm Barry Loewer. Um, I'm now a professor emeritus. There was what should I say? You know, everybody grows older, but I didn't realize I was growing older until about a year and a half ago. I always thought I was about 25 years old, but of course that wasn't true. But if I think back to when I was in high school, I became interested in philosophy and science, particularly physics and mathematics. And then I went to an undergraduate school. And there was a particular story about how I got interested in philosophy of science. I was taking courses in physics, history, and statistics, in which in all those courses, the concept of probability came up. And I couldn't understand. They were talking about it in somewhat different ways. And I asked the teachers, what is it about? What is he talking? What are probabilities? And they said, well, we use probabilities here. Go to the philosophy department. So I went to the philosophy department, and there was a good philosopher of science there. His name was Joseph Epstein. He didn't publish that much, although he published some things, so he's not so well known. But he was really great. And he said, well, I don't know the answer to that question. Philosophers have a number of different answers, but I can get you on the path. So I've spent most of the rest of my career in philosophy thinking about, well, many things, but in particular, always come back to the question of what is objective probability, what is subjective probability, what are chances? And maybe we'll talk about that a little bit today. I went to graduate school after I went to Amherst College. It's a college in Massachusetts. Very great, good college for liberal arts. And then went to Stanford University. I went to Stanford University in part because I had great logicians there, very famous mathematical logicians and mathematicians. Paul Cohn, discoverer of the independence of the continuum out of forcing it to prove the independence of the continuum hypothesis, and Georg Kreisel and various other people. And I realized that that was not my field. I really should be in philosophy of science. And I ended up doing really modal logic, but I still maintained an interest and kept an interest in philosophy of science. Then I got a job at the University of South Carolina. I was there for about 10 years when I got a job at Rutgers, and I've been at Rutgers ever since then. And I got back to my main interest in philosophy of physics and philosophy of science about 35 years ago, particularly when I met someone who became my lifelong best friend, David Albert, who's a philosopher of physics now at Columbia. And he and I work together. In fact, we're teaching a seminar together right now at Rutgers on statistical mechanics, the arrow of time, the nature of laws and chances. So I wrote a book I published a couple of years ago called Laws and Chances, What Breathes Fire into the Equations. It's about, I would guess one would say, the metaphysics of laws and chances. What are laws of nature and objective probabilities about? What makes them obtain? And various views have been developed within philosophy and adjacent fields. Physicists also have views about these things. Interestingly, no one has written a history of the concept of laws of nature. There have been histories of the concept of objective chance on probability. Ian Hacking is one author, but there are other authors too, but objective chance. But no one has written really a comprehensive history about what happened with the notion of objective laws, of laws of nature. So I want to talk about that for a minute. So the way we think about laws of nature now really only came into existence in the 17th century with Galileo, Descartes, Boyle, and related people. Of course, everybody has recognized that there are patterns in the world, recurrent patterns. Biology is full of them. The weather is full of them. The heavenly bodies are full of them. But nobody really inquired into what makes it the case that they hold, in part because it was taken for granted either that it was God that made for regularities, or in the Aristotelian tradition, it was in the nature of things to exhibit regularities in various ways. So in the nature of biological, of a cat to chase after mice.
Mhm.
Okay, these are not very satisfactory views. In the 17th century, Descartes actually held a theological view. He thought that there were simple mathematical principles that described how material bodies moved, particularly the heavenly bodies, but also bodies on Earth like rocks and projectiles and pendula and so on. And that these mathematical principles described how God makes things move. So really, matter was passive, but God made things move. Newton may have held a similar view. It's very unclear what Newton held. His spokesman Clarke seems to um, uh, hold such a view at some places, but I don't really know. I'm not a Newton scholar. I can't say. And this is a question that should be looked into carefully. But anyway, philosophy really didn't address what makes laws of nature until really the 20th century. The first book I know of written about laws of nature, there may have been others, but I don't know what it was, by David Armstrong, called What is the Law of Nature? So he held the view that laws were something over and above the ordinary events. Laws were relations between universals, according to Armstrong, that made for certain regularities. So this view is a so-called non-Humean view. Hume, much earlier, held a view about causation in which causes were not anything over and above recurrent patterns. So on a Humean view, the recurrent patterns just recur. There are no further explanations of them in the sense that there's something that makes them hold. What is an explanation is finding regularities that are very comprehensive and that organize all the other regularities, that unify the other regularities. That's a Humean view. The great Humean in the 20th century was the greatest philosopher, in my view, of the 20th century, David Lewis. So Lewis had a view about the nature of laws, which I'm going to describe in a minute. Stop me if I'm going on too long, incidentally.
No, this is great. This is great.
Okay. David Lewis, he held his view Humean, although Hume himself didn't have as far as I know, he didn't have a explicit view about laws. He certainly knew about Newton's laws of classical mechanics, but he didn't really ask what makes them hold. But I suppose he would have held a Humean view because he was David Hume. But David Lewis was explicit about it. According to David Lewis, what the world is fundamentally is the distribution of fundamental properties in space-time. Lewis held that fundamental properties were what he called perfectly natural properties. We don't know what they are, but we can make guesses at what they are. Maybe charge, maybe electromagnetic field values are fundamental properties or magnitudes. Lewis held that they were instantiated at space-time points, and they were something which philosophers technically call categorical. A property is categorical if the property itself doesn't imply the existence of any regularities, any patterns. The regularities come from the way the properties are distributed in space-time. So Lewis's view was that there's a candidate systems, ways of systematizing the distribution of all the fundamental properties throughout all of space and time. And good systems should try to optimize balancing informativeness and simplicity. And a best system of the world's Humean mosaic is a system with best balances, informativeness, and simplicity. Informativeness is how much the system says about the Humean mosaic. Simplicity is, as you might guess, mathematical simplicity in the system. Now, Lewis thought that candidates for best system have to be formulated in a language whose simplest predicates only refer to perfectly natural properties. If he didn't have that restriction, then his view would collapse into triviality. Easy to see why. I didn't speak quietly right. If he didn't put some restriction, the restriction he put on isn't the only one you might put on. I actually want to put a different restriction. Okay. Now, Lewis's view, so people who listen to this podcast may not realize just how ambitious and incredible David Lewis's view was. David Lewis was a real metaphysician. He had a view about what fundamental reality is like. He thought that the actual fundamental reality is this Humean mosaic. Every other truth about the world is made true by what's going on in the Humean mosaic. That is to say, which regularities are laws depends on what's on the Humean mosaic, on the best systematization of the Humean mosaic. I'll explain what chances are in a minute, but the chances also, what objective probabilities are, will depend on the Humean mosaic. Causal relations also depend on the Humean mosaic. So whether one thing causes another. one event causes another. It depends on patterns in the Humean mosaic. So he was very Humean about it, like that. Whether we're sitting here talking to each other depends on what's going on in the Humean mosaic. Everything depends on what's going on in the Humean mosaic. Now, we're not here to talk about David Lewis's philosophy in general, but I can't bring him up without mentioning that Lewis thought that not only did the actual world exist, but many other possible worlds exist as well. So the actual world is just one of many possible worlds. If you're just encountering this for the first time as a listener to the podcast, you may think, this guy is out of his mind. But you have to read David Lewis's work to realize he has very good reasons for all of these views. I disagree with many of them, but I was drawn into his views because his arguments for them are very, very good and convincing. And really what he's really interested in doing, what's at the bottom of what he's doing, is making sense of what's going on in science, and particularly in physics. Okay, that's really the driving force. So in order to make sense of that, because physicists talk about laws and causation and chances, he thought that he had to come up with the kind of metaphysical view that I'm explaining. Okay, I've been talking quite a while now, Kyriakos. Ask me a question.
No, this is really interesting, and it's quite a fascinating thing for me because it's a world of, well, knowledge that I haven't explored as much, and so most of the things I hear are new to me, which is great. You said that initially you found very interesting um, um, when you went to school and studied different topics,
Mhm.
probability and the difference between objective and subjective probability. Um, could you explain us the difference between the two? And is there a certain definition of the word probability that you like in particular?
Yes. Okay. It may take you 5 or 10 minutes for me to do it, but I can do it.
Mm-hmm.
So, okay. So around us in nature, there are some regularities, like Venus occurs in the sky at various times, and people can map out when Venus will occur. And, we can learn pretty regular. In fact, even astrologers learn about that. Okay, but astronomers certainly learn about it. And the motions of the moon and the motions of the tides are very, very regular. These are what we might call lawful. But some things that occur in nature don't seem regular at all. At first, in fact, it might seem like hurricanes. They occur at certain seasons, but no one can predict when a hurricane will occur. Or, for example, the stock market. No one can predict exactly which days it'll go up and which days it'll go down, or how much it'll go up or how much it'll go down. Or politics. There's a kind of randomness in these kind of things. Okay, now if you were just somebody, let's say, living in ancient Greece, the ancient Greeks had a word for events that are sort of chancy. I think 2K was the word for it. And that was different from events that are regular. These seem like they belong to different realms. The regular events are lawful. And like I said, God was thought to control the laws. Whereas the chancy events just, happen. Maybe those events that God just doesn't pay attention to. So he lets it happen this way or that way or who knows what. Okay. Um, so in the 17th century, um, a chance mainly was played a role in gambling as it does today. So if you can get interested in dice, well, there's certain chances you throw the dice, certain chances you'll get, you know, snake eyes when you throw a pair of dice. Um, uh, so the actual history I'll mention it briefly, but you want to read about it. A good place to read about it is Ian Hacking's book, The Taming of Chance. Is that the story was that there was a gambling game, and that I think it was the Chevalier de Mer, if I remember correctly, uh, is involved in this gambling game, and the king's police broke up the gambling game before it was finished, so they stopped it, but they didn't know how to distribute the winnings because it depended on how the likelihood of the various ways in which the game might finish. So the Chevalier de Mer went to Pascal, who was a friend of his, who was an important mathematician, Blaise Pascal, and he asked Pascal to think about it, and Pascal figured out what should be done. And he basically invented the mathematics of probability. And the mathematics of probability started in gambling games, but the notion of probability sort of took root in people's minds, and it extended from gambling games to other things. And by the time the 19th century rolled around, probability started being used in physics, and particularly in statistical mechanics. But probability, as Hacking says, was always had two faces. He called it a Janus face concept, after the Roman god Janus with two-faced coin. We meant by that one face faced the objective world, because it looked like things going on in the world made probabilistic claims true or false. But the other face faced your mind, because it told you what degrees of belief or how strong your belief should be in various things. So if you're throwing dice and you discover the objective probability, objective chance of the dice landing on a sum total of 7 is 1/6, I think, then your degree of belief should be, you know, not very high, but not very low. It should be 1/6, actually. So people discovered that you could measure degrees of belief by probabilities as well. So that's subjective probability. Subjective probability has to do with degrees of belief. Objective probability has to do with the world. But really, a, a probability has to do with both of these things. Some people who thought about probability thought they could take subjective probability off on its own, and thought that you only have to talk about subjective probability, only talk about degrees of belief. The most famous thinkers about that were Bruno Di Finetti, who was an Italian mathematician, and Leonard Savage, who was an American mathematician. So they thought that really in science or in physics, when you're talking about probability, you just have to talk about degrees of belief. But that can't really be right, because scientists use probabilities to give explanations about what will happen. And some degrees of belief are right, and some of them are wrong about the world. So there must be something objective about it as well. So the question is, what is the objectiveness about probability? Well, I think, and for me to talk about that, I have to go back to talk about laws a little bit more. So I didn't really finish off this story about laws. So there was this non-Humean view about laws that was David Armstrong's. I told you about that. Objective relations between, we call a relation of necessitation between universals. And then there was the Humean view of David Lewis's that I explained a little ways. But there have been other non-Humean views about probability. The one which is most vivid and goes closest back to the old theological view, except God isn't involved in it, is due to my friend and sometime colleague. He lives down the block from me, actually, Timothy Maudlin. Some of you may have heard of Tim Maudlin. So his view is that laws are primitive elements of reality. So he disagrees with Lewis in this way. He agrees with Lewis that there might be fundamental events in a space-time, but he thinks that over and above the fundamental events are these things he calls laws. They kind of replace God in his view. Because when I say this to him, he wants to hit me because he doesn't believe in God. But it seems to me that what laws are doing in his view is they're doing the work that God did in the old Cartesian theological view. What they do is they take the events at any time and they evolve them to make events at subsequent times hold. So his view involves a primitive directionality of time, as well as laws evolving events in time. And there are other non-Humean views about laws, but I think I'll use up too much time talking about them, so I'm not going to do that except for one. One view goes back to the old Aristotelian view. The old Aristotelian view about laws is that laws are within the fundamental properties, or that the regular patterns were in the fundamental properties. So there weren't laws over and above the ontology, but properties themselves make for regularities. Properties are what is sometimes called powers. So the property of being an electron, uh, being charged, being an electron or being an electron, has the power of repelling other electrons, because they also have the power of repelling electrons in a particular way, according to a particular principle, namely Coulomb's law of electromagnetic charge. I don't think this powers view works out very well in contemporary physics. So this is a technical matter. I don't want to go into it very well. But I do want to mention it before we come to talk about chance. Because when somebody asks, what in the world make objective chances hold? Well, the first thing you would think of is that chances have something to do with frequencies. So we think that the chance of a coin landing heads is a half, let's say, when it's thrown. Because if you throw the coin many times, it'll land heads about half the time. And once the mathematics of probabilities was sort of understood a bit in the 19th century, Bernoulli proved a famous mathematician, Jacob Bernoulli, proved famous theorems called the strong and weak laws of probability or of chance, which basically say that if events are what are called independent, that means what one event occurring doesn't change the chance of another event occurring. If the events are independent and the same event occurs at the same chance, and they're independent and they're repeated over and many, many, many times, then the frequency of the event occurring will be equal to the chance of it occurring. So I'm not explaining this very well right now because I'm a little tired. But so, for example, with a coin, there's what we might call a trial or experiment. Flipping the coin, the event is the coin landing heads. And if we were to flip the coin over and over and over again, then if the chance of the coin landing heads is a half, since the flips are independent, then the frequency of the coin landing heads will be near a half. It pretty surely won't be exactly a half, but the chance of it being very close to a half will be very high. But of course, this tells you nothing unless you make the connection between chance and degrees of belief, between the objective and subjective phases of chance. If you make that connection and you think that your degree of belief should equal the chance, then you should say, my degree of belief in the coin landing very nearly a half should be just about a half. Okay, well, that's good. So maybe chances are just frequencies. But that can't be exactly right, because sometimes there's a certain kind of experiment which is only done a finite number of times, and the frequency is different from the chance. So maybe you might think, well, there are infinite frequencies. But no events are actually done infinitely many times, maybe, in the actual world. So that can't be right. So you might scratch your head a bit and say, gee, chances have something to do with frequencies, but they're not exactly frequencies. What could that be? So now I want to tell you one view about what they are connected to the non-Humean powers view. And it's also somewhat connected to Tim Waldron's view. The view was enunciated by a very famous philosopher of science. I'm not going to talk much about him because I will get off on a tangent. But you're in London now, right?
Close, yes.
So he used to live in London. Do you know what I'm talking about? He was the most famous philosopher of physics, science, not physics, really, of science in London. And he totally infiltrated the philosophy of science world in England during the 1940s, 50s, and 60s. So this is now a question for you.
40s, 50s, and 60s. Huh.
I don't
Um,
think he died until the 80s, actually. I'm not sure.
I'm not sure who you're talking about.
He's who were the most famous philosophers of science of the 20th century?
Well, the most famous physicists that, well, the
Not
first names that
physicists,
comes to mind,
philosophers of science.
philosophers of science specifically, um, most famous
What do you
ones.
think about that? I got to open my door.
Okay.
Vicky, come down here. My cats wanted to come in, so they're here now. Can you see my cats?
Nice. Nice.
They
Yes,
were
yes, I
knocking
can
on the door.
see you in the background. That's so cute.
They're
Oh,
beautiful, yeah. Actually,
wow.
can you see the picture on the
That's
bed?
really nice.
You know that's a picture of?
Yes.
Who?
I was wondering, I'm not sure. I was wondering if
That's
it's,
David Lewis.
yeah, I was wondering if it was David Lewis. I was kind of
Okay, but
scared of
you haven't answered
suggesting
my
that.
question. I'm not talking about David Lewis now. So David Lewis, I think, is the most important philosopher of the 20th century. But this guy was thought to be the
Yes.
most important philosopher of physics, philosopher of
Is it
science.
Popper? Is it Karl
Yes,
Popper?
Karl
I'm not sure.
Popper, of course.
Karl Popper, yeah.
Yeah.
Falsification and
The people always talk about Popper and Kuhn. Kuhn was really a
yeah.
historian, but Popper, Masua was thinking about. They came in because they wanted to play.
Uh, that's so nice.
So they would know the answer to these questions because they're around me all the time. Anyway, so Popper held a view about objective probability called the propensity view of probability. By that he meant, and it's kind of like the powers view or the old Aristotelian view, that the coin has a propensity that comes in degrees, just like an electron has the power to just repel other electrons. The coin has a propensity of 1/2 to land heads. So this seems to be a kind of non-Humean view about chances. Um, we're not here to be a technical philosophers, but I think it's absolutely terrible view. But David Lewis's view about laws can easily be extended to cover objective probabilities in a Humean way. Can I explain how that works?
Yes, please.
So let's think, for example, remember Lewis's basic idea that what laws do is they systematize or organize patterns.
Mhm.
Well, some patterns can't be organized by laws, but they can be organized by supposing that the events that occur over and over and over again have a certain objective probability of landing, of occurring. Let me give you an example with a coin. Suppose there was a world in which all there was in the world was outcomes of coin tosses. Let's call them 100 100 or heads tails. Let's call them 100 100 1 1. So you see a long outcome, and it looks sort of what we might call crazy or random. I'll talk about randomness in a more scientific, more technical way in just a second. But they look crazy. There's no pattern. What can you say they happen? But then somebody notices, look, if we suppose that um, the ones occur with a chance of 1/2 or whatever it is, 1/3 or whatever, no, ninth, whatever. and that the events are independent, then we would expect to see patterns like the ones we're getting. That we expect the long sequences would be just about like what we're getting. Bernoulli's law would tell us that. So Lewis said, or this is actually my version of Lewis, would say that's the way that we can come up with an account of what objective probability is, which is Humean. But now you have to say, how is it going to be in the system? And the idea, and this is basically taken from Lewis, but it needs to be refined and developed, is that you look at a Humean mosaic and you add to the candidate best systems a probability function, which works kind of like the way I described it. And the best systematization should be the one that makes the actual world likely. So there might be different systems, and one system makes the actual world very, very, very unlikely, so that's no good. Another one makes it a little bit likely, so maybe that's okay. So you just
Yeah.
compare them. The one that beats out, the one that makes it the most likely, which still may be very small, is the one that is the best systematization of the world, and that determines what the objective probabilities are. That's a very
Mhm.
ambitious account, and to really show that it makes sense, it takes a lot of work. I'm writing a book about this now. Okay, no one's actually worked it out in detail, but it's a very interesting, great idea because I think it's an answer to my question. So I think I've succeeded. I'm not sure ready to leave the Earth and shuttle off my mortal coil, but I think I've now come to something like what I think is an answer to the question that I asked my teacher in in college. So I think developing this idea right, and it's like I said, I'm writing a book now about it. My book actually is called The Mentaculus Vision because I apply it to something I call the Mentaculus, which I don't know how much time we have left, but we can talk about that
Oh
later
yeah,
on.
I'm free all evening, so don't I
You're going to
time is
edit
not an
this
issue for
too.
me.
Oh, you
Sorry.
edit it. So okay.
Hmm.
Well, I'll run out of steam though after a while.
Oh yeah,
So
whenever you're tired, it's fine. But
So let's see.
I'm
Is my
time is
T-shirt
limited.
visible from where you see? What does it read?
Mentaculus, the probability map of the universe.
That's right. So this T-shirt comes from a summer school institute that I've run a few times, where basically graduate students and postdocs and other and young faculty came to learn about laws and probability. I've run it mainly in a couple of places, but mainly at there's a university in Budapest, Hungary, called the Central European University. Okay. Now, just as a side address thing, which you can edit out if you want, the Central European University was founded by a philanthropist named George Soros. But the Hungarian government is as terrible as the American government is, and it basically kicked out the Central European University about 5 years ago. But the summer school has continued to meet in Budapest. So is meeting in Budapest. I've taught this, I don't know, since 2002, maybe. I've done it about 4 or 5
Hmm.
times. Last time, maybe in 2022, I think this was. And um, okay, so what is the Mentaculus? Ah,
Before we
as
go
you
to
can
the
tell, I'm interested in a
Mentaculus,
lot of things like connected. Why don't you ask a question?
yeah, no, before we go to the Mentaculus, which I definitely wanted to ask you about, I'm struggling to understand why the word mosaic was chosen. Why, uh,
Why what was
um,
chosen?
I'm struggling to understand why the word mosaic was chosen in
Mosaic.
the
Ah, that's
yeah.
Lewis's word. Mosaic is just a pattern, a tiles with a pattern. Usually, of course, they're beautiful mosaics, but the world's mosaics may be very unbeautiful. Remember, what the patterns are fundamental properties. Most of the possible worlds are completely the patterns are completely crazy.
Mm,
They're are no way of systematizing it, either by using laws or laws with chances. They're just completely crazy. We happen to live in a world which is patternless, because we couldn't live in a world without patterns. So that's a sort of what's called an anthropic argument for why the world is patterned. It's not a strong enough argument, but you get the idea.
Mm.
Um, so one could ask the question, why does the world have patterns in it?
Mm-hmm.
And if somebody were to ask me that question, I would say, that's the deepest question I know of. And I don't think I'm going to live to know the answer. Of course, someone who believes in God might say, God made the world patterned. Someone who believes in laws, well, he could say that the laws make the world pattern. Someone who believes in non-Humean laws could say that the non-Humean laws make the world patterns. But what's the next question you're going to ask that person?
Who 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 made the non-human laws?
No, these are non-Humean laws, right?
Mm.
Who made the laws, right? Why are
Mm-hmm.
there laws? If there are
Mm-hmm.
many, okay, okay. So this is like an ultimate question. It's the kind of question that only philosophers will really spend any time with. I mean, children ask this question sometimes because children are sort of natural born philosophers, at least some of them are. Um, my children were when they were born, and when they realized that both their parents were philosophers, they immediately decided, I ain't going to be a philosopher, whatever I do with my life. So
Uh,
one of them became an artist, and the other one is becoming a political scientist.
nice.
Um,
Wow. Can I ask you about the Mentaculus? Also, I'm interested in the etymology of the word. Is the word two parts, or is it
yeah, I'll tell you
one?
where the word comes from because that's an easy, amusing story. Also, I have to explain why we're talking about it and how it's connected to laws,
Mm-hmm.
because a listener to your podcast will have no idea. Okay, so let's go back to the 19th century. In the 19th century, um, the science of thermodynamics was developed. It was developed because people really wanted to know and develop steam engines, and really practical reasons, and why ice melts, and why gases expand, and why smoke disperses, and various things, and like that. And these are macroscopic phenomena. They're not the fundamental phenomena that Newtonian physics can deal with. Now, classical Newtonian mechanics thought that the fundamental properties, the Humean mosaic, except it isn't really our Humean mosaic because Newtonian mechanics isn't correct. But the Newtonian world just consisted of particles moving around. So the fundamental world was just a lot of particles, many, 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 10 to the 80 something particles, many of them, moving around on trajectories in various ways in conformity with Newton's laws. Newton's laws are very simple. There's only really one Newton dynamical law that determines how the laws move. Every student in high school learns it. They don't know that they're learning so much when they learn it. And that's the law F equals ma. It says that a particle moves, accelerates, depending on its mass and the force exerted on it. So all particles have a mass, and that's something like its weight, but not quite. Weight is proportional to, to mass. And force is something else. Well, Newton also had, besides this dynamical law, force laws. Now, Newton's laws about how particles move, and of course, since everything there is made up out of particles, so it describes really how everything moves. Newton's um, uh, laws then can only be completed by having not only F equals ma, but also force laws. Well, one of the force laws, also many people know, is the gravitational law. It says that for any two particles, they attract each other depending on their mass and how far apart they are from each other. You write it down as a little equation. Now, Newton's laws had the following consequence, that if a particle is moving at a constant velocity, nothing has to keep it moving. It just continues to move at that constant velocity. That's quite different from what Aristotle thought. Aristotle thought for something to move, you have to keep pushing it, because that's the way it looks on Earth. But that's because when things move, and if you, let's say, roll a ball on the ground, not only is the force of pushing the ball, getting the ball moving involved, but there's also friction. It keeps the force of friction that keeps the force stopping to move. The force of friction ultimately is just electromagnetic forces. So also electromagnetic forces. Once you have electromagnetic forces and gravitational forces, that's not all the forces there are, but that's enough to talk about what's going on macroscopically. But now let's go back to steam engines and thermodynamics. What is a gas? It consists of many, many, many particles. So Newton's laws will describe how those particles move. Well, we all know that a gas, let's say cigarette smoke is often the example, that when it comes out of the cigarette, it's sort of concentrated, but it disperses into the air. So the particles are moving, so that it disperses. Or to give another example, take a little bit of ice and you put it into warm water, it'll melt. The particles of the ice will disperse into the water. Or maybe another vivid example, take a drop of ink, put it into water, it'll spread. But it'll spread in a kind of what looks like, we might say, randomish way. Now you might wonder, are there probabilities that describe how this happens, how all these things happen? And one of the greatest physicists who ever lived, two of them, figured out that there was a way to describe how these things move using probability. The physicists were James Clerk Maxwell, who also invented electromagnetic theory, and Ludwig Boltzmann. What they did was to say, look, if we make a certain assumption about how the probabilities of where the particles are and what their velocities are at any time, then together with the Newtonian force laws, we could describe probabilistically where they're likely to be later. And the assumption they made was that if the particles are concentrated in a place at the beginning, then it's very likely, given this probability assumption, that they'll be spread out later. It's possible they won't be. In fact, there's a probability that the ink, when you put it in, won't disperse. But that probability is tiny. It's minute because there are so many particles in the ink. There's even a small probability that the particle, when you put it in the water, it'll spell out a word. It might spell out Trump go away or so, who knows what. Okay. But these are tiny, tiny probabilities. Most likely it'll just spread out in some usual way in which we see it spread out. Some way we might call typical.
Mm.
So what probability assumption is this? Well, it's the probability that every position and velocity that the particles could be in, given the constraint that they're located in this particular place, is equal to every other, the probability of being in every other place. In other words, the simplest probability you could think of, so-called uniform probability distribution. There's some technical mathematics about this, which we don't need to go into. Okay, so if we bring this back to the David Lewis view about probability, we might say, if the actual mosaic was a Humean mosaic, then we should just add to it this probability law, because we now then could connect macroscopic phenomena with fundamental microscopic phenomena in a way that's useful to human beings, because human beings could never know where the particles are or how they're moving exactly at any moment. Of course, with Newton's laws, if you knew exactly where they are and how they're moving, you could predict exactly where they'll happen later. Laplace, I don't know if everybody knows, but Laplace famously, I don't know if this is a true story, but Napoleon asked him to tell him something interesting, or asked him about physics. And Laplace told him that, well, in classical Newtonian mechanics, if you knew exactly where every particle was at now and how it's moving now, you could predict where every particle will be at later times and earlier times, given F equals ma and the force laws, um, and the properties of the particles, their masses and charges and so on. And then you might be able to read off whether Napoleon would win or lose the Battle of Waterloo, because that would depend on what the particles were doing at that time, right? Because the particles moving one way, he wins. Particles moves another way, he'd lose. Now, as a matter of fact, the particles moved so that Wellington defeated him, and that was the end of Napoleon's career, basically. Okay, so what Boltzmann did was to give the basic idea for how to connect the macroscopic description of the world and the special sciences description of the world with a fundamental microscopic description of the world. Now, this is an idea which I think is understood by more people than me. I basically learned it from reading David Albert's book, Time and Chance. Well, he doesn't quite put it the way I did, but I became very enthusiastic about this idea. And other people have it too. I'm sure Richard Feynman, the famous physicist, had it, and other people have it. But I'd say I'm the philosopher who's now really promoting this idea that the way to connect the macroscopic with the microscopic is with this idea from statistical mechanics. This makes statistical mechanics one of the most important things you could learn, at least as a philosopher, in physics. They're the fundamental laws, they might be Newtonian mechanics or quantum mechanics, quantum field theory or string theory or something like that. But then you have to connect this fundamental physics to the macroscopic world, which we describe in sciences like biology and economics and really parts of physics, for that matter, like astronomy, because astronomy describes how planets move. But planets are made up of many, many, many degrees of freedom, many parts. Okay, now you want to know where the Mentaculus comes from?
Yes,
Now I'm going to
please.
tell you. Okay, it's an interesting, amusing story. There's a film directors named Jonathan and Ethan Cohn. They've made many, many great movies. Probably their most famous movie, I think, is Fargo. It won a number of Oscars, I believe. But the movie that I like most by them is called A Serious Man. It's actually about a physicist living in Minneapolis. This was where they're from, teaching at some university, maybe the University of Minnesota, I don't know, who's going through a midlife crisis. And in the film, there's a minor character who's scribbling in a book. And somebody asks him, "What are you doing?" And he says, "I'm composing the Mentaculus." So then the person asks him, "Well, what's that?" And he says, "It's a probability map of the universe." So when I saw the movie, I realized that what I'm doing is making up a probability map of the universe. So I decided to call the project I'm working on the Mentaculus. Now, as chance would have it, so to speak, my son was going to the same school that Ethan Cohen's daughter was going to, so I had his email. This was like, oh my God, 13 years ago. So I sent Ethan Cohen an email and asked him whether I could borrow this word. And you sent me back an email that said, yeah, of course I can have it. In fact, he really came from a friend of his when he was in college at Princeton. He went to Princeton, um, uh, who was writing a book, uh, a sort of philosophy book with this name, but he never finished it. And that's where he got the name, and he used it into his film. And so I could use it. He was fine with that. And he and I got to know each other. I wouldn't say we became friends exactly, but we met for lunch numerous times and exchanged emails because he was interested in what I was doing and I was learning about what he was doing. So that's one of the great things about philosophy. You can get to meet people like film directors. We have more time. I can tell you about all the other people I've met as being a philosopher. It's an amazing career for me. So that's where the word mentaculus comes from. So what is a mentaculus? Well, it's the fundamental laws of the world together with this probability assumption, together with something else. Because if all else we had is we added this probability assumption, it wouldn't work out well. Because first of all, we'd have to know at what time to add the probability assumption. If we added it now, at the present state of the world, it would give pretty good predictions going forward to the future, but terrible retrodictions about what happened in the past. Because given the ice cube put in the water, it would predict that the ice cube would melt, but it also would predict that the ice cube was larger and was a bigger ice cube in the past. And we don't think that. Why is that? That's because the fundamental laws of physics, Newtonian laws, but also quantum mechanical laws, are what are called time symmetrical, temporally symmetric. Anything that can happen in one temporal direction, as far as the positions of things are concerned, can happen in the other direction with the same likelihood. Okay, so you got to get rid of this. So how to get rid of this? Well, the idea was thought of really by Boltzmann himself, but later by other people, by Arthur Eddington had this idea, famous writer, and Richard Feynman had it, but it was explicitly put down by David Albert in his book Time and Chance, and he called it the past hypothesis. It's a cosmological hypothesis. It's the idea that there's a law which says that the universe was very, very concentrated, just like the ink blob of ink, at a certain time. Now, we call that time the earliest time. But I'll explain to you why we don't have to call it the earliest time. It's going to earn its name as the earliest time. I'll explain that, why is that in a minute. But a very concentrated state is said to have a very low entropy. Now, entropy is a somewhat technical notion, and I don't know if you want me to explain it in this podcast.
Please do. Please do.
Okay. So the entropy of a macroscopic state depends on the measure of how many microscopic states make that macroscopic state hold. The smaller the entropy, the fewer microscopic states realize or make that macroscopic state hold. There are many less ways in which an ink blob can be in a small region than spread out throughout the water. Okay, now when I'm saying many, I got to be really careful here because there are literally infinitely many for both of those. So it's not just counting many. You have to introduce you have to use measure theory, and you have to introduce a mathematical measure. Now that's more complicated than I think you want to be explained in this podcast. The basic idea, we could go along for this. If everything was finite, we could use the counting notion of measure. That there are the lower the entropy, the fewer the fewer the microscopic states that can make true, or this usually is realize the macroscopic state. The bigger the entropy, the more. The highest entropy state is called the equilibrium state. And in fact, when the state of the system goes into equilibrium, if it's an isolated system, then it's very likely to stay in that state. Why? Well, because it's very likely for any state that's not an equilibrium state that its entropy gets bigger. Of course, it's a possibility that its entropy gets smaller, but it's very, very likely that its entropy gets bigger. Now, the claim that the entropy of a state gets bigger is called the second law of thermodynamics, but it really has to be modified to be a probabilistic law. To say that the entropy of an isolated system doesn't necessarily, it's not lawfully it'll get bigger, just that it's very, very, very likely to get bigger. And for an ordinary macroscopic system, since there are so many particles or so many degrees of freedom in it, the likelihood is very, very, very close to 1. Nevertheless, there's a certain probability, certain chance that that ice cube won't melt. It'll just stay as an ice cube, even that it'll take water from the air and grow bigger. Okay, that won't be isolated in that case. But okay. So once you've introduced this thing called the past hypothesis, and that's what David Albert called it, but he shouldn't have called it that. He should have just called it the low entropy hypothesis. He should have just said that the universe had a very, very low entropy at a certain time. We call that time 14.3 billion years distant from us. But in fact, he didn't even have to do that because of some other issues about space-time, which we don't want to talk about now, but the physicist Ernest Mach realized you don't have to talk about how far in time events are from each other. You just need the sequence of events. But I shouldn't even say that because I'm not going to explain it right now. Okay. So let's just talk about distance in time. 14.3 trillion years distant from the present, entropy was very low. Once we have that, we see that that time is going to be the past. Why? Because if we use the probability, the Boltzmann probability distribution, what it'll predict is that towards the past, things become more and more constrained. So if you see the ink halfway down through the water, the Boltzmann probability distribution will predict that it's very likely that it was much more concentrated towards the beginning, because there the past hypothesis would basically play the role of, or actually the claim that the ink drop was concentrated would play the role of the past hypothesis. Okay, so when you really think this through, and it's explained in detail in David's book Time and Chance, it will explain why it is that we can know so much more about the past than we can about the future, and in so much more detail. Why you can know that Caesar crossed the Rubicon 2,000 and something years ago. Why? Well, because we can have records of that. But we can only have records because the probabilities going towards the past yield that result. Because when we say, given that we have books with such and such and such marks in them, then it's very, very likely, given other things about books and so on, very, very likely that what they say in it is true, and that Julius Caesar crossed the Rubicon at a certain time. So records are formed. So I think anybody listening to this will not really believe what I'm saying because it's very, very fantastical and ambitious. It says that this probability map of the world is what underlies the existence of records. It's what makes for the possibility of records of the past. Once we have the past hypothesis added to the probability distribution. So what the Mentaculus is 3 assumptions. One is the fundamental dynamical laws and whatever the ontology is. Newtonian mechanics, it's particles and particle trajectories, and the dynamical F equals ma law, or Hamilton's equations. It's a fancy way of expressing F equals ma. And the force laws. Hamilton's equations include the force equation, including the force laws. Also, the Boltzmann probability distribution, and also the past hypothesis that the universe had very low entropy 14.3 billion years from now. Given these three assumptions, they will entail a probability map of the world. And my claim is that that probability map of the world, and this is what my book is about, that probability map of the world is enough to recover why it is that we can know so much more about the past and the future. It's enough to recover why it is that we say things like, if I were to throw the ice cube in the warm water, it would melt. So we say something about what would happen towards the future, but we can't say something about if I were to throw the ice cube, what had happened in the past to the ice cube. You can just say, well, the past would have been exactly as it was, I guess. At least macroscopically, it would be. Now, in fact, I have a very explicit theory about how counterfactuals work, and causation is very closely related to counterfactuals. David Lewis had the idea that an event C causes an event E, just in case if C had not occurred, E would not have occurred, or something like that. It's more complicated. And that's right. And he had a view about how the Humean mosaic made for that counterfactual to be true, and so for that causation claim to be true. I think his view about that wasn't exactly right, but I have a probabilistic account of counterfactuals, which then I can use to explain what causal relations hold. Now, in fact, the idea that causation and probabilities are closely related, that's a pretty widespread idea in statistics now. So the statisticians develop what are called causal models, but they're not philosophers. They're not really looking at the question, what really makes the causal claim hold or not in the world? They're rather interested in the question of how we can find out whether causal claims are true or not. And these are two different questions. The second question is an epistemological question. The first question is what we might call a metaphysical question. It's very easy to confuse these two questions. And in a podcast, I'm not going to really get people to really understand the difference between them. But in statistics, we're interested in finding out whether one kind of event causes another kind of event. In metaphysics, we're interested in what makes it the case that one kind of event causes another. It's the second question that I think this Humeanish account that David Lewis developed, if it goes in my direction, not in Lewis's direction, has an answer to. Statistical model theory is a way of getting at the epistemological question, and I think that fits in very nicely with the counterfactual account that I've developed now. There's a philosopher who's interested in the metaphysical question who's written a book recently. You might be interested in interviewing him. Have you heard of him, David Papineau? Do you know the name?
No, but I
He lives not
definitely
far from you.
research him.
Do you know if you've heard of him, David Papineau?
No, but I will research him. I will written his name down.
He lives in your neighborhood. He teaches at I think King's College, I think.
Mm-hmm.
Okay, maybe he's emeritus now. He's my age. I don't know, but I know him pretty well as a friend. I'll see
Mm-hmm.
him at the end of April. But he's just written a book on causation. He has a book, an probabilistic account of causation. He doesn't quite connect it to counterfactuals, but I see that the two accounts pretty much can be made to fit together.
Okay.
Okay, now here's another question. And this is the last thing. I'm going to run out of steam after that, and you're going to have to ask me a question.
Mm-hmm.
Here's another basic thing that you might scratch your head and wonder, why can you influence the future, but you can't do anything about the past? The saying in English is don't cry over spilled milk, because you can't do anything about what happened yesterday. Now, that's basically true. Okay, but I said before that the laws of physics are temporally symmetrical. So why can these two things fit together? Well, the reason is that we can only act at the macroscopic level. And at the macroscopic level, we got to use these probabilities with the past hypotheses. And the probabilities work in such a way that there are probabilities about what might happen in the future, which you might say leave the future open. Just like when you put the ink drop in the water, you don't know exactly how it will spray in the water. There are many different possible ways in which it might spray in the water. But when it's in a particular place, there really is only one way in which it could have gotten to that place, or there's only one likely way it could have gotten to that place. Now, that's not an exact analogy, but it gives you the basic idea. So the future is sort of open probabilistically, but the past is sort of closed probabilistically as far as the objective probability is concerned. As far as subjective probability is concerned, that's not true because we don't know a lot about what happened in the past. So subjective probability is open, but that has nothing to do with what we can do about the past. What we're interested in, what we can do is we're interested in objective probability. Okay, does that make sense to you, Kyrianos?
So, in terms of objective probability, there's nothing that we can do about the past, you said. But I didn't understand with subjective probability.
Oh, because do you know what Julius Caesar had to eat before he crossed the Rubicon?
Tell me
Does
one more
anybody know
time.
that? There
I'm
are
not
probably no
sure.
records of that. No. And so you may have a subjective degree of belief about it. You're probably pretty sure
I
that he
see.
didn't eat certain things. He didn't eat, I don't know what to say, um, a Chinese,
Yeah.
dim sum, Chinese dim sum, because
Mhm.
that wasn't available in Rome at the time. But he might have had a rice and grain dish. I don't know
Mm.
if they ate pasta in Rome then or not. I don't really know. You might have had pasta. I don't
I
know.
understand.
Okay. So that's a subjective degree of belief. Okay. Okay. But of course, if you knew, which or if anybody knew, which nobody can know, as Laplace said to Napoleon, the exact state of the universe now, then that determines what Julius Caesar had to eat, assuming that the fundamental laws are temporally symmetric and that deterministic. Okay, now are the fundamental laws deterministic? Well, that's another question we didn't really delve into. Well, Newtonian laws are deterministic. What about quantum mechanics? Many people think that quantum mechanics is not deterministic, but that's not exactly right. But that's a whole other interview, so we don't want to get into that now. We could talk about quantum mechanics. I'd advise you to interview someone other than me. Well, I know a lot about it. David Albert is more of an expert, or Tim Moreland is more of an expert, or David Wallace is more of an expert. They all have different views about it. Um,
I'm talking to Tim Modeling next week, actually. So I'll
really?
yeah, I'll bring it up on our episode. Can
He
we?
likes it. He disagrees with me about laws and chance radically. And
Mm.
don't tell him that I said his view was theological. He'll get very angry. And when Tim gets angry, it's not a happy scene. Okay, don't repeat that either.
That's funny.
But his views are different. Very respectable, interesting views. I kind of tried to explain it a little bit before. His views about quantum mechanics is he likes David Bohm's views. I do too. I'm not sure they're right. I have other possibilities too. But David Bohm held at the fundamental laws of quantum mechanics. One way of holding his views is that they're literally deterministic. Probabilities were introduced, or objective probabilities were introduced in his view, kind of like the way objective probabilities are introduced into statistical mechanics. However, Tim Maudlin doesn't really like objective probabilities. He likes to talk about what he calls typicality instead. And I don't know whether you could interview both of us together if that's allowable to have an argument over that. Um,
We can
that's very
definitely
interesting.
do. That would be really interesting for me too.
He's busier than me because I'm semi-retired. He's still teaching full time. So I don't
Mm-hmm.
know that he'd want to do it. And I don't know. Like I said, he's a friend and he lives down the block, but we actually haven't talked for about a month and a half.
Mm-hmm.
So we're not really close friends, but so I'm not sure.
That
David
would be
Albert,
really interesting.
did you contact David Albert?
I think I sent him an email maybe a few days ago. I um I am unsure whether I got a response, but I would
So,
definitely be interested in talking to him.
so both these guys make for great interviewers, for great interviewees, much better than me. Um, but David Albert is the greatest. If
Well,
you know,
I think
yeah,
you also explain things extremely well, and and the way you correlate each topic, and it makes sense to me, and so I don't get lost in the story of the information you're giving us. So I think it's something that people appreciate for sure.
well, thank you, because we covered a tremendous amount of territory. Basically, we covered material which would take me a year to teach in a graduate seminar. But of course, we get into it in much more detail than we talked about it today, and students would ask questions, and we'd make sure they'd understand it. Right now, I'm teaching a seminar with David Albert that covers part of this material. You're welcome, actually, to come to the seminar tomorrow, which we'll talk about
Yes,
some of this.
I was going to mention I would love to do that for
Send
sure.
me an email reminding me. I'll
Yes,
send you the
yes.
Zoom link. It's a Zoom link to it. And I'll see you because you'll be known as Curianos. Probably just a K will come up. You can come up so we can see
Mm-hmm,
you too. But we have
mm-hmm.
about 12 or 8, 10 people to come to the seminar, and then about 20 people who come by Zoom. So it's I don't know how many people come tomorrow, but it'll be
Yeah.
interesting tomorrow because
Mm-hmm.
a philosopher named Mark Lang, who's also an interesting person, who's a colleague at Rutgers, who has a non-Humean view about laws, which he connects to counterfactuals. So he will talk at the beginning of the seminar. Then I will talk about why he's wrong, and or why I have a different view, and then I'll begin talking about objective probability in the seminar.
Okay, yeah, that sounds amazing. I wanted to ask you just so things in my brain, I just make sure I understood things correctly. So when we say we have low entropy in contrast to high entropy, it we're thinking about microscopic and macroscopic, and
Hmm.
so if we have a small number of ways in which these microscopic things can be configured, then we have low entropy. But if we
That's right.
had
Configured to make
that,
that macroscopic state. Okay, let me go a little bit further. The notion of entropy actually has a number of different uses in various places. In computer science, it has a view. In a certain definition, in statistical mechanics, in information theory, and so on. But they all can be connected to each other in the way we're talking about. And sometimes entropy is assigned to the microscopic state rather than to the macroscopic state. But basically, the most fundamental way of thinking about it, the way you always come back to, is the way I explained it. Entropy is a property of the macroscopic state, and it's given by, as you just explained, the number of microscopic states they could make for that macroscopic state. The lower the entropy, the fewer the microscopic states made for that macroscopic state. The more information a sentence or proposition has about the world, the fewer possible worlds make that proposition true. So if if you're comfortable talking about possible worlds here, or should I explain what I'm using the notion?
it's good to explain what we mean by possible worlds.
Okay.
Yes.
Okay, it's very simple, and David Lewis, he wasn't the first, but he made this notion very, very widespread and popular in philosophy. Think about the fundamental world. We're talking about the Humean mosaic. Well, there are a lot of ways the Humean mosaic could be. One way it could be is it would make me a billionaire. Unfortunately, it's not like that. Another way it could be, it could make my cats come back in the room now. Maybe they won't come back. They got bored. One way it could be is the way it actually is. So the proposition, any proposition that I make, any sentence, an indicative sentence that's aiming to be true or false, it'll be true in some possible worlds and false in other possible worlds. Does that make sense?
Mm-hmm.
Okay. The more informative a sentence is, the fewer possible worlds it's true in, because it is excluding all the others. Let's do this in a very, very limited way. Let's talk about where the king is on a chessboard. Now, what are the possible worlds on a chessboard? They're the possible squares. There's 64 possible worlds. The king might be located on square 1 or square 2 or square. Those the squares are numbered, from the lower left-hand corner. So if I told you that the king was located on square 13, I'd be telling you a lot about where the king is located, right? But if I told you the king is located on a red square, I would be telling you something, but not a lot. Does that make sense? If I
Mm-hmm.
told you it was located in the upper right-hand quadrant, I'd be telling you more than by telling you it's just on a red square.
Mm-hmm.
But I still wouldn't be telling you as much as if I told you it was located on square number 13.
Mm-hmm.
Okay. So that's how the notion of entropy is used in information theory. You see, it's very closely connected to how it's used in statistical mechanics.
I see. And
And
what? Sorry, please
no, you
go
go.
ahead. Sorry. Um, I was just trying to understand when it comes to, well, more from a philosophical point of view, when it comes to determinism. If we, if we, what's your views, and what does studying objective, subjective probabilities, what does studying the arrow of time, what do these things tell us about, if about determinism and free will?
What do objective and subjective probability tell us about what?
What does studying the arrow of time and studying probabilities, do these things tell us anything about free will and determinism and
Oh, about free will. Well, I've
uh,
written a little bit about that. Of course, determinism is the view that the fundamental state of the world and the laws determine what the state of the world is at later times and earlier times. That's what I explained earlier.
yeah.
Laplace said to Descartes, to Napoleon, about what Newton's laws are like. And I don't know whether the fundamental laws of our world really are deterministic, but I think it's possible that they are. And I don't know whether they're really temporally symmetric, but it's possible that they are. Let's suppose that they are. Like, that's the way classical mechanical or Newtonian laws are. That's the way the laws in certain versions of quantum mechanics are as well.
Mm.
Given the complete state at any time, the state at any other time is determined by the laws. Okay. Okay. Now, you ask, how's that connected to the arrow of time? Well, the arrow of time has to do with how the macroscopic state evolves. That's what we talked about earlier. The macroscopic state evolves probabilistically. So the macroscopic state is open probabilistically to an extent, while the past is closed in a way probabilistically as far as objective probability is concerned. Okay. Well, that's the arrow of time, isn't it? The arrow of time is
Mm-hmm.
that you can influence the future, but not the past. That we can know much more about the past than the future. that
Mhm.
causes occur before their effects. All of this comes out of the Mentaculus. Now, how to
Mhm.
connect this to free will? Well, some people thinking about determinism have thought that if the fundamental laws were really deterministic, then there couldn't be free will.
Mhm.
Because to act freely is to be able to choose to do this or that, depending on my will. But if the fundamental state of the world in the past, together with the laws, determines on whether I choose this or choose that, how can it be that my will is free? Now, Kant famously worried about this, the philosopher Immanuel Kant.
Mhm.
He thought it was the biggest mystery. But he thought somehow it must be that we can have free will even though the fundamental laws are deterministic. But there are some philosophers who've given arguments that they think show that if the fundamental laws are deterministic, then we don't have free will. A famous argument along these lines was given by the philosopher Peter van Inwagen, and it goes like this. Look, you can't do anything about the past, can you? Like you can't change the way things were a week ago or a million years ago.
Mhm.
You can't do anything about the laws, right? But the past and the laws entail what the future will be, so you can't do anything about the future either. It's a pretty strong argument. But wait a second, there's a way around it. Because if you look at the Mentaculus, what the Mentaculus says is that maybe you can't do anything about the macroscopic past, but it doesn't mean you can't do anything about the macroscopic future. It's true you can't do anything about the microscopic past, but nobody ever wants to do anything about the microscopic past in detail. You want to do something about the macroscopic past. Now, of course, if you do something about the macroscopic past, that would do something about the microscopic past, but not in any way that you would know anything about or that you care about. How are we going to express this? Well, we do it in terms of counterfactuals. That's what we mean by can do something about. Um, can I make a choice to choose whether I raise my left hand or my right hand? Yeah, if I were to choose to raise my left hand, then I would raise my left hand. If I choose to raise my right hand, then I would raise my right hand. These are counterfactuals, what I would do. But if I choose now that I would have raised my left hand in the past 10 minutes ago, it would make no difference. But it doesn't mean that the counterfactual, if I had, when I look at the counterfactual, if I had chosen to raise my left hand 10 minutes ago when I didn't, it'll turn out to be false. But if I had chosen to raise I'm sorry, I'm not explaining this right. If I were now to raise my left hand a little bit from now, even though I don't, I still could have. What that would mean is the microscopic past would have been a little bit different from the way it actually works. But the macroscopic past would be exactly as it actually was. That's why I can't do anything about the past, but it doesn't mean that I can't do anything about the future. Now, I don't think I explained this very well right now, and all I could say is I wrote a paper about this in a book called uh, Time's Arrows, I think, edited by a couple of Argentinian philosophers, um, whose names I'm not going to remember right now.
I can find them and put them on the screen.
Yeah, it's easy to find. And, my paper is called the uh, the Mentaculus meets the consequence argument. The argument I gave you before, why about Van Inwagen gave, is called the consequence argument, and I'm sure why the Mentaculus gives you a way around it.
So we cannot change the microscopic past, but
it
we,
does it can counterfactually depend on us.
which allows us to change the macroscopic future.
The macroscopic future.
The
Let's make
macro,
sure
yes.
we're using micro. So we cannot. You're using the word change. I wouldn't use the word change. I would use what would happen if we were to make various choices.
Okay.
Um, what- but I'll use change as usual. So we can change the microscopic past, but we can't change the macroscopic past. We can change both the microscopic and macroscopic future. Let's say both of those can counterfactually depend on us, what we choose to do. But the macroscopic past does not counterfactually depend on what we choose to do. The microscopic past can depend on what we choose to do. Now, there are other complicated things connected to what I'm talking about, but this is a whole other interview, really.
Mm. Yes, this is very, very, very interesting. I will go read your paper. Is there anything we haven't talked about that you'd like to uh, say? Or
Well, I'm running out of steam. I'm interested in many, 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 many things. Things, uh, novels and poetry and art and visiting. Like I told you, I've never been to Cyprus, but I'd like to. What's it called? Heraclion, like, make me pronounce it right. It was the famous city in Cyprus. Isn't it in Cyprus? Or maybe it was in Crete. It was in Crete. I'm confused. What was
maybe
the famous ruins in Cyprus? What are they called?
the famous what?
There are ruins there in Cyprus.
Ruins. Um, well, I'm not sure which one specifically you're referring to. Um, we have, well, some interesting historical sites to visit in Cyprus is Hyrokitia, which is a small, almost village that's, well, it's that people lived thousands of years ago, and it's quite well maintained, and
Uh-huh.
it's quite the contrast because you see these modern houses, maybe 15 minutes, uh, drive 15
No,
minutes
no
away, and then you
electricity
see,
there.
yeah, no, yeah, and then you see this small little kind of maintained area
Well,
that's
I've
really,
never heard of that. That sounds very interesting. I know that there's ancient Greeks settled in parts of Cyprus, and of course Cyprus was settled by Turkish tribes a long time ago. So I know there are,
yes,
so the place I was thinking of is not in Cyprus at all. I was confused, and I actually have been there. It's in Crete. What happens when you get
Heraklion
old?
maybe, I'm not
Yeah,
sure.
that's what I was thinking of. And you just get
Heraklion.
confused about names.
Hmm.
But so you say, what am I interested in? Well, I've traveled a lot in my life. I've been in many, many places, but I've never been to Cyprus. I've never been to Japan, but I might have the opportunity of going to Japan this coming summer. I don't know whether it'll happen, but I've been to China, to India, to
Mhm.
Africa many times.
Do you find that traveling, when they say the traveling broadens your horizons, do you feel that when you go to other places that you can explore different cultures and almost
Yeah.
grow your mind?
Yeah, I'm not any expert. I don't know that much about it, and I didn't get into it that much. I mean, when I was in China, it was present day China, and I visited the Great Wall, and I was in a city. I didn't like China very much. The city was very polluted. I was in. I went there for a philosophy conference, and I stayed a while longer and traveled. But I didn't like China, but I don't really know it. When I was in India, can I tell you about when I was in India? Because that was like one of the great
Hmm.
events of my life.
Hmm.
I was invited to give some lectures in philosophy at a Tibetan monastery in India. It's actually not in northern India where most of the Tibetans are, but in not far from New Delhi, maybe about 150 miles from New Delhi. But you got to go through the countryside to get there. And it was a monastery. And it was very interesting to go there. And I traveled to India a bit, and I saw some wildlife and met people in the Tibetan monastery, and I met other people there too. And now I discovered, we're not just talking about human being to human being, right? Just two
Mm-hmm.
guys talking together, except I'm much older than you. When I
Mm-hmm.
was your age, I was very shy. Now, you're not shy because you're willing to do podcasts, but I would never do a podcast when I was your age. I would just have my head in books all the time. But now I'm this age. Now, when I take a taxi, I always talk to the taxi cab driver. Usually in New York
Mm-hmm.
City, he's from another culture. Talked to taxi cab drivers when I've talked to, I don't take taxis all the time, but just the other day I had to, and I talked to a taxi cab driver from Senegal. I talked to a taxi cab driver from Bangladesh. So
Mm-hmm.
you find out about them, and it's very interesting. Incidentally, have you been to New York City?
I was asked that today by my counselor. I have been to the JFK airport numerous times because I come to Austin, Texas sometimes, and I train Brazilian Jiu-Jitsu, which is a martial art. But I've never actually left the airport in New York.
Well, it's a big airport. I tell you, when yesterday I had occasion to walk through a big part of New York City, and I kept
Mhm,
thinking, I'm so lucky. It's the greatest place because there are so many cultures here. You walk down one
mhm,
street, just one street, see a Chinese restaurant. I mean, this is, of course, one way of seeing it. It's not just the restaurants, but this one way it makes it very obvious.
mhm,
A Chinese restaurant. Then, Georgia, the part of Russia, or just the old Soviet Union is now a separate country called Georgia. You see a Georgian restaurant. And then you see an Indian restaurant. Then you see a Mexican restaurant. Then you see a Peruvian restaurant. I mean, it's just amazing. And you meet people of all sorts of different cultures. But London is like this too, right?
mhm. I think there's something really healthy when it comes to this diversity. And I think you can, well, like at my martial arts gym, we have quite the diverse group of people because the owner is Yusuf, is from Pakistan and he's Muslim. And then the um well, my housemates that also teach there are, well, one of them's a Buddhist and the other one's a Christian and the other one's an atheist. And so you get all these different characters with all these different belief systems, and then when people come in and interact with each other, then you learn from each other and you
Yeah.
wrestle with your pre-existing beliefs and ideas, and then hopefully we don't get we stay friends and then we just grow as people. And I think this is really nice, and it's something that I love Cyprus, and I think it's a great place, but I feel that it was something that was missing from my life, this interaction with completely different cultures.
Well, I
I
think
think it does
London,
something.
what I've heard, I don't know London that well. I've been there a few times, and I believe I will be there also in June.
Mhm.
But um, I think it's very much like New York in this way. But New York is even more like that. Why were you in Austin?
So I don't know why things came to be this way, but Austin, Texas has arguably the best, or at least some of the best, martial arts gyms in the world, specifically for Brazilian Jiu-Jitsu, which is a grappling art. It's similar to Olympic wrestling. And so
Oh,
I was,
really? I know you. Yeah, I know you're a wrestler of a special sort.
yeah,
Yeah,
yeah.
you
So,
told me that. I don't. I
mhm.
didn't know that about Austin. I do know Austin. I've been there a number of times. I've lectured at the University of Texas, and I have a friend I went to college with who is a retired English professor at the University of Texas. And I've been there a few times, and I think it's it's not like the rest of Texas. It's a very special little town. It's very, it's not like New York either, but it's a very nice place. And
Mm-hmm.
I didn't know the wrestlers. My one of my roommates in college was a wrestler. Actually, did I tell you that?
No,
Did I
that's so
mention it?
cool.
Yeah, he was what he was one of Amherst College's best wrestlers. He was on the wrestling team. I've lost contact with him. I don't know what happened with him. I don't even know if he's still alive. Actually, I'd like to find out. Um,
Yeah, I spent around six
can
months
I
in
tell you one of the
Texas.
best stories of my life since we're talking about this?
Uh-huh.
And I'm really
Uh-huh.
interested in telling stories. It's a story from when I
Uh-huh.
was in college. So this friend of mine, his name is Howard Zeiler or Howard Zeiler Aldendorf. He was on the wrestling team. So he wrestled at about 145 pounds because they do it in college, they do it in pounds.
Mm-hmm.
But his natural weight, V8, would be about 180 pounds. So he'd be spending a lot of time losing weight to maybe it wasn't that much. I don't know how he did it, but I remember him spitting out all the time to lose weight to wrestle. But he was very, very good at wrestling. So I know because when I asked him about it, he had me on the floor in like 1 second. Okay.
Mm-hmm.
He was also into jujitsu and stuff like that. Okay. So one day we were walking across the campus and he and I were walking together and it was a snowy kind of, snow was on the ground in Amherst, Massachusetts, snowed a lot there. And we bumped into a couple of people from the football team, two big guys. And I sort of didn't get out of the way. I bumped into one of them and he kind of knocked me down. And I got up and said, "You shouldn't do that." He said, "You want to fight?" And I couldn't fight with this guy. He would knock me out in a second. And Howie said, pushed me aside and said, "You don't want to fight with him. He's an expert." But me, I'm not an expert in anything. Howie said, "Fight with me." So I said, "Okay." So this big football guy went after Howie. And within a second, Howie had him on the ground.
Mm-hmm.
So that's, if you're a good wrestler, I'm sure you could do the same thing, right?
Yeah, well, it's magic. It's amazing. I remember the reason I fell in love with grappling and martial arts is because I used to be nearly 100 kilos, which is 225 pounds, and I used to have a lot more muscle. And I wasn't obese. I was quite muscular. I was just lifting a lot of weights. And I went to this class, this jiu-jitsu class, when I was, well, 3.5 years ago now. And this 60 kilo Chinese guy, my friend from Cyprus, Evgeny, and this other girl, my friend Maria from Cyprus, because I was in Cyprus when I started. Um, they just beat me up constantly, and
At just 60 kilos.
I was just so inspired. So a lady half my weight and a guy nearly half my size who's been training. The Evgeny was training maybe 3 months more than me, which is he maybe choked me out maybe 5 times in 5 minutes. So I was just like, okay, there's two ways I can see this. Either I can get offended or I can get really inspired. And I just got so inspired. I was like, wow, this is so cool. So yes, I've been quite obsessed. It's one of my obsessions ever since.
So your story is a little bit like mine, except you went on to be a wrestler. I went on, didn't do anything like that. You know what my sport was? We didn't really talk about this. I was a very good table tennis player. Do you know what table tennis
Oh,
is?
really?
Yeah,
Uh-huh.
I actually won. I wasn't like super good, but I was the southeastern for a while the southeastern men's over 30-year-old champion.
Oh, that's so cool. So is it quite tiring?
Well, when I used to play, I used to have to train for it. So yeah,
Is
and
it
I weighed a lot less than I weighed now, and I can't play now anymore. Just like I can't play the piano anymore or anything like that because you get old, your body doesn't. I was thinking the other day, it's a very philosophical thought. A person remains the same person in some way by accumulating memories. Your memories grow and get bigger and bigger and bigger. You also have the same body in some way, but your body also changes. Your body kind of, as you gets older, you can't do what you did before. I used to be able to run. I wasn't a good runner, but I could run 5 or 10 miles. I can't do that anymore. And your body falls apart in other ways you don't want to hear about. And ultimately you die. But your memories kind of accumulate. You also lose memories too, but some memories stay. Right now, I'm also sort of trying to write down my memories over my life. It's why they're so ready to tell you my stories, because I think nobody else is going to be interested in them, but I hope my children and my grandchildren are interested in these.
Well, there's a lot to gain when I think it's lovely to hear personal stories and also just life experiences from you. And I always welcome these kind of conversations with other guests I have because I think, well, it gives a human aspect to our conversation. And also I think people that are very influential in different fields, well, I want to understand how, okay, what are their personal experiences, and and a lot of the times these personal experiences show you, okay, how does this person think? What can I get from their way of
Yeah.
thinking, their perspective? So it's always everything like I learn from people is useful personally.
Right. So look, we got to stop because I haven't eaten lunch
Yeah, sounds
and I'm
good.
exhausted and I got to prepare my seminar, which you might come
Sounds
to
good.
tomorrow. The
Yes, no,
seminar will talk
I
about a
will.
lot of the stuff we talked about today. So
Perfect.
you hear about it again. And I don't know what you're going to do with these podcasts, but I hope you edit this a lot because, we went all over the place. And I like doing it. I enjoyed meeting you. Like I said, I'm going to go to a conference in Dublin, Ireland in June, and I might go to London first. If I'm in London, maybe I'll email you. I know you're not outside of London, but maybe you'll come to meet me there if you want
Yeah,
to.
yeah, yeah. No, I'd be very
We'll
happy to do that.
we'll have
I'll put
lunch
a
or something.
reminder on my. I'll put a reminder on my
I don't
calendar
know. This is like
to.
totally unworked out yet.
Yeah.
I've been a little bit sick this week, so I gotta make sure I'm healthy to do it for
Hmm.
all this traveling. So we'll see. But I gotta say goodbye now. So we had a good
Yeah.
time.
No. Perfect.
Say hello to Tim for me when you talk to him.
Sure.
His personality is a little bit different from mine. Think it's safe to say, but he's very, very smart. He's super smart. He's one of the smartest people I've ever encountered. So he will tell you things very clearly, but he will disagree with me. But stay back. Don't be convinced by anybody right now. Okay.
Sounds perfect. Thank you so much for your time. Just one thing
Okay.
before we finish. So I usually, the way I structure the podcast, I make an intro and then I use chapters so people know maybe someone's really interested in the past hypothesis, for instance. So where at the point you specifically speak about that, they can go to that part. I usually don't edit bits out unless my guest specifically requests me to
No,
edit
I didn't
specific
say anything
bits
I'm
out.
embarrassed by, but do whatever you
Okay,
want to
cool.
do. Do
Okay,
whatever you want to
cool,
do
cool,
with it.
cool.
Okay.
Cool, cool, cool. Sounds
Okay.
good. I usually just keep it. I think people appreciate it very raw. Cool. So thank you so much for your time, sir, and I'll see you at
Okay.
your
So thank
seminars
you.
tomorrow.
I had
Excited
fun.
to learn.